You know how power companies always seem to know just how much electricity we're going to need during a heat wave? Or how Wall Street tries to predict where the market is headed? Well, it all boils down to one thing: forecasting. And for decades, it's been a really, really tough challenge. But now, a new technology, one that was actually born in the world of language processing, is completely changing the game. We're talking about transformers. And in this explainer, we're going to break down exactly how they're revolutionizing the art of seeing the future. All right, so here's our roadmap. We'll start with the core challenge: why looking far ahead is so darn hard. Then we'll take a look at the classic models, the old playbook. After that, we'll introduce the big disruptor, the transformer, and watch what happens when the new school faces off against the old guard. From there, we'll dig into the hidden costs of all this new power before finally taking a peek at what the future of forecasting holds. So let's kick things off with the fundamental problem itself. I mean, predicting tomorrow is tough enough, right? But what about next month or even next year? The difficulty just grows exponentially. And look, this isn't just some abstract puzzle. It's a huge hurdle in pretty much every industry, from climate science to managing global supply chains. Now, the technical term for this headache is long-range dependencies. It's basically the struggle to connect something that happened way in the past, like, say, a big sales promo back in January, to an outcome that's way off in the future, like your final sales numbers in December. And your traditional models, they are notoriously bad at connecting those dots. So how did we used to deal with this? Well, before this big disruption we're about to get into, the world of forecasting had a pretty established playbook, with two main kinds of players on the field. On one side, you've got your classic statistical models, like ARIMA. These are the old school workhorses. Their beauty is in their simplicity. They're easy to understand, but they really start to stumble when things get complex or when patterns aren't just a straight line. On the other side, you've got recurrent neural networks, or RNNs, like the famous LSTM model. Now, these are smarter. Think of them as having a kind of memory, which lets them spot much more complicated patterns. But they have a critical flaw. They process everything one step at a time, in a sequence. Not only is that slow, but more importantly, it means they can literally forget crucial info from the beginning of a long timeline. And this is where our story takes a sharp turn. Enter the transformer. Now, this new architecture was actually designed to understand human language, but it turns out it has this one unique ability that makes it perfectly suited to crush that long-range dependency problem. So what's the secret sauce here? It's something called the self-attention mechanism. This is the transformer's superpower. Instead of reading a timeline step by step and maybe forgetting the start, a transformer looks at the entire history all at once. It can instantly figure out how important every single data point is to every other data point, no matter how far apart they are. This isn't just a little improvement, it's a completely different way of thinking. It sees the whole picture all at once. And the innovation didn't stop with the original transformer. The base model has now evolved into a whole family of specialists. You've got the informer, which is optimized to handle insanely long sequences of data super efficiently. Then there's the Autoformer, which is brilliant at automatically breaking down data into its core trends and seasonal patterns. And you have the TST, which is custom built for all the little quirks you find in time series data. Okay, so all that theory sounds great, right? But how do these new kids on the block actually perform when the rubber meets the road? How do they stack up against the old guard on real-world data? All right, let's dive into the numbers. These columns, MAE, RMSE, MAPE, they're all just different ways of measuring how wrong a prediction is. You can think of it like a golf score. The lower the number, the better the performance. And you can see a really clear story here. The classic ARIMA model has the highest error. The neural networks, LSTM and GRU, they do better. But then you get to the transformer family and the error rates just plummet, with Autoformer coming out on top with the best accuracy of the whole bunch. And this graph? This shows us why that accuracy is so crucial, especially over time. See, on the left, for really short-term predictions, all the models are kind of close. But look what happens as we try to predict further and further out. The error for the old models just shoots up. But the transformer models, they stay remarkably flat and accurate. Their advantage just gets bigger and bigger the further into the future you try to look. So to really put a number on it, we're talking about a massive 25 to 40% reduction in errors for those really tough long-term forecasts. In this world, that's not just a small step up. That is a full-blown revolution. Okay, so we've seen the incredible upside, but all this new power doesn't come for free. Nope. Like with any major leap forward, there are always some pretty significant trade-offs to think about. So here's the first big one. On the one hand, you have that incredible, superior accuracy we just saw. But on the other hand, you have the cost. A transformer can be up to 8 times slower than a simple ARIMA model, and it needs way more powerful and expensive hardware to run. So yeah, you get a much better answer, but it's going to cost you in both time and money. The second trade-off is all about understanding. While that cool attention mechanism can give us some clues about what data the model is focusing on, the whole thing is still pretty much a black box. It's much, much harder to explain why it made a certain prediction compared to the simple, transparent logic of an old statistical model. It's kind of like you got the right answer on a math test, but you have no idea how to show your work.
So, with all that in mind, the incredible strengths and these notable weaknesses, where does this technology go from here? What's next on the horizon for forecasting?
Well, the research community is already all over these limitations. People are building hybrid models, trying to get the best of both worlds, the accuracy of transformers and the clarity of older methods. They're laser-focused on making these things faster and cheaper to run. And there's a huge field called explainable AI that's dedicated to cracking open that black box to make these amazing tools more transparent and trustworthy. And this all brings us to the big final question. What we're seeing here is a fundamental shift in our ability to predict what's coming. With models that can see further and more clearly into the future than anything we've had before, you just have to wonder, what are the monumental challenges, the ones we once thought were unsolvable, that we're going to tackle next?